solve questions regarding this. We're going to start with simple questions, then we move towards the difficult questions. So it says that the distance between the first and the sixth node is 30 centimeters. First, let's visualize this. So let's make the wave. So first node, second node, third, fourth, fifth, and sixth. And most definitely the stationary wave actually looks like this. Okay, so from first, second, third, fourth, fifth, sixth node, the distance is 30 centimeters. He's asking you about the wavelength. What's the wavelength? So let's count them. So this is going to be one wavelength, lambda. So this is going to be second wavelength, lambda 2. And this is actually half a wavelength. So I can say that this is actually 2.5 wavelengths being covered in a distance of 30 centimeters. You take this, divide this, and you'll get your answer as 12 centimeters, which is option D. So this animation or this understanding has helped you to understand what the question is asking you and how to visualize the questions at least. Now let's move to this one. He has given you the frequency, he's given you the length of the column as well, but he's asking you about the speed. Be careful, one thing that he has done for you, this is in centimeters and the speed's in meters per second. So you have to convert this into meters before you solve the question. Anyways, how many waves are being formed? So we have one complete wave from this point to this point, it is lambda, and from this point to this point, lambda by 2. So I know that within a distance of 210 centimeters given to me, I'm covering a distance of 1.5 wavelengths. So lambda comes out as 210 divided by 1.5. Let's do that. 140, but this is centimeters. I will add a factor of 10 raised to the power minus 2 to make this into meter per second. So I want to find speed. V equals to F lambda. F is given to me in the question as 80 hertz. So 80 multiplied by 140 multiplied by 10 raised to the power minus 2. For God's sake, please remember that centi has a power of 10 raised to the power minus 2. If you want to go back to grade 2 and class 2 and class 3, you can do this method as well, 140 divided by 100 to convert it into meters. But please, you learn these prefixes and it will make your life much easier. So if you solve this, your answer should be 112 meters per second. The students who are going to put in the full values, for example, who are not going to convert this and going to multiply 80 with 140, they will get 11,200. So in hurry or in speed, they will mark option D as the correct answer. But please, that is going to be centimeters per second. He is asking you about meters per second. So be careful. Again, a question, he says that there is the distance is given to you, the speed is given to you, is asking about the frequency. No problem. So starting from this point and ending at this point, I can see that the wave actually looks like this. Like this. So how many wavelengths are there? Very clearly, we can see one full wavelength and lambda by 2. So this is going to be 1.5 wavelength being covered in 30 centimeters, right? So I can find that the lambda is going to be 30 divided by 1.5. Let's try that. So this is going to be 30 divided by 1.5, I think 20. Yes, so 20 centimeters of wavelength. Now, since we're working standard unit, this has to be converted into meters because the speed is also in meters per second. So V equals F lambda. Speed is 330. F is what we want to find out. Lambda is 20 into 10 raised to the power minus 2. For an A-level student and for a class 2 student or class 1 or even KG, this should be 330 equals to F into 20 divided by 100. Go back to the Stone Ages if you want to do this. So F is going to come out as 1650 hertz. So this is going to be your answer as option A. Okay. This is a very common question in A levels as well, and it is difficult for the students to understand. Please notice that this is actually an open end, and this is proving to be a closed end or a fixed end. Okay, let's see how to solve this. He says that the first loud sound he hears is at 83.5. I'm going to shift this column into a sideways diagram so that it becomes easy to visualize. So when the water column was this high, when it was from the ground, of course, this is the ground. When the water column was this high, 83.5, a student heard a loud sound, which means that an antinode was made over on this side. An antinode was formed and a node was formed over here. Now, the second loud sound that the student hears is when it is actually 17. Now, they let water out so that they can change the length of the column. When they're trying to do that, they're trying to find out the next harmonic that they can find. So they realize that when they are actually from the base, when they're actually 17.1 centimeters away, when the water level is at this point, they hear a loud sound again. Now go back to the open closed position. This was my first case. This was my second case. There is no other possibility. So what could have been formed between these two levels? What could have happened? So comparing with the original level, there has to be a wave that is going to be formed like this, and there has to be a wave that is going to form like this, because this is the next harmonic that is going to be formed. Now, when you take the difference between the two heights, you realize that this one was at 83 and this one was at 17.1. So if I take a difference of both of them, I can find the distance between these two levels, which is actually lambda by 2. So my lambda by 2 comes out as 83.5 minus 17.1. My lambda comes out as 100 and I think 32.8 centimeters. I'm working with meters per second. I have to convert this into meters. I've shown you how to do that. So let's find out the frequency. So frequency is going to be the speed, which is 340, divided by the lambda, which is 132.8 into 10 raised to the minus 2. When you find the frequency, this is going to be 256.01 hertz, and we know that this is going to be 256. Let me draw this for you again, a bit larger situation. So first loud sound word is heard under these circumstances from the center position, which is 83.5. Yes, 83.5. The second sound was heard when this was at this level, which was 17.1. Okay, so what could have formed at this point? We know that for the second situation, second stage of harmonics, form a wave that goes like this. So we know that if we take the difference of this much, that is actually equal to lambda by 2. That is why we made this equation. I hope that this is clear. You will find a similar question like this repeated many times. He asks you about the conditions required for the stationary wave. We have already discussed that at the very beginning of the lesson. We need the same nature of the wave. We need the same speed. We need them to have the same frequency, and most importantly, they must be moving opposite to each other. If one has to come from this side, the other has to come from the other side. He says that they have an oscillator over here. Of course, notice that this is a node. This is a node. Frick Stents produces nodes. He says that it is being vibrated at 250 hertz. The speed is already given to you. He says that at time t equals to t1 at a certain instant in time. What is this string that is being shown? So at a certain instant in time over here, this is where he has paused the situation. That, let's say, for the sake of example, this is point A, and after this, I think one complete wave, falling crest. Okay, so after one complete wave and the falling crest, this is point B. All right, so we make a standard graph at this point. So this is where he has actually stopped the time, and from this point onwards the time will be counted as he mentions in the question. Okay, all right, I'm going to keep this video paused at this point because this is going to come in handy later. All right, he asks you calculate the distance between AB. So indirectly he's asking you to find out B equals to F lambda. Let's do that. We have the speed, we have the frequency, we can find the wavelength. So we have 12 meters per second. Lambda is supposed to be found. Frequency is 250 hertz. Lambda comes out as, now I'm taking this in millimeters. The answer is going to be 48, I think. 48 power minus 3. You will get 0.048, but I'm writing this down as standard form, which is 48 into 10 to the power minus 3, which is millimeters, 48 millimeters. So this will be 48 into 10 to the power minus 3. In the marking scene, you will see this one. Doesn't matter. This is also acceptable. So now we need the distance from A to B. We have to be clever about this. This is not the answer. You see, this is one wavelength. From this point to this point, this is 48. From this point to this point, how much would this be? This is actually half a wavelength, right? So what you can do is you can multiply this 48 with 1.5 wavelengths, because this is how it is, and find the answer, which is going to be 72 millimeters. Okay, so this will be 72 millimeters. Multiply this with 1.5. Now, this is where the question gets interesting. This is where the problem is going to start arising in the visualization. And this is the most important part that I've seen for stationary waves, at least. He says, sketch the position of the string between A and B at times t1 plus 2 milliseconds. Now, what are we going to do now? We have the frequency, which is 250 hertz. Let's convert this into time period. So 1 over 250 gives me a time of 4 milliseconds. Now, that is interesting. He's asking me at 2 milliseconds, which is half of the frequency, half of the time period. So what's about this? And if I open this up 5 milliseconds, as 4 plus 1 millisecond. This also produces 5 milliseconds. So what about this one? And what's this? What is the similarity? What's happening? Now comes the part where you need to be very focused at this point. Please be very focused. This is point A, and this is my point B. This is the wave that we are actually discussing. This is the mean position of the wave. And let's see what happens. What is the meaning of this time period of 4 seconds? I've calculated the time period to be 4 milliseconds by calculating this as 1 over 250, which was the frequency. What is the meaning of this for a particle that is living on the wave? It means that this particle will take 4 milliseconds to complete its life cycle. How is that? It takes 2 milliseconds to come down and then takes 2 milliseconds to go back up again. So it has completed its life journey in a total time of 4 milliseconds. Now, if I had to calculate how much time it will take to come back to the mean position, most definitely it's going to be half. Because for the full journey, if this is 2, for half the journey, it's going to be 1 milliseconds. This is where the problem is. Okay. So he asks me at the very first beginning that what's going to be the position when it is actually T1 plus 2 millisecond. T1 is the situation where the wave is standing right now, the blue wave, this wave, wherever it is. If I add 2 milliseconds to this, and I realize that what my wave has to do, what does it have to do with this? How will I calculate this? I figured out that it takes 4 milliseconds to complete one life cycle. So what's going to happen after 2 milliseconds? Let's take a look at its life. So if this is where it is already, in the next 1 millisecond, it will come down. In the next 1 millisecond, it will come down over here, constituting the total time of 2 milliseconds to come down, and then 1 milliseconds to go back up again, 1 millisecond to go back to the original position. So 2 milliseconds to come up again, which makes one life cycle of this particle equal to 4 milliseconds, which is your time period. So if he's asking you 2 milliseconds later, what's going to happen after 2 milliseconds? I realize that this is going to look something like this. That the wave or the particle, these particles will come down, these particles will go up, right? And after 2 milliseconds, where are they supposed to be? So after 2 milliseconds, they are supposed to be at this location. The whole journey is 4 milliseconds, one side is 2 milliseconds. So these particles will come down to this position at the new location like this, and these particles are going to go up at this point and then at this point. That is what's going to happen. Now let's see whether does this animation go to that situation or not. You can pause the video, take a screenshot, and let's see what's going to happen. So I paused the video at this point, that this is the current situation of our system, right? So let's see what happens. This has happened after 2 milliseconds. So from this point, it came down in 2 milliseconds, and in the next 2 milliseconds, going to go back up again at the starting point, right? This is our answer for the first part. What is going to happen after 2 milliseconds? So from the current position, it's actually from the mean position. Don't draw the mean position, actually it's the answer of the next part, but anyways. So it is going to be exactly reflected in the opposite direction. The particles have moved from this point to this point in the 2 milliseconds. So he says, mark this wave as P. So we write P. Then we have the next question in which he says what's going to happen at 5 milliseconds. Now he's being clear about this now, right? So in 4 milliseconds, I know it's going to come back to the original position. If it had started from this life, it will come down in 2 milliseconds, go back up in 2 milliseconds. It's starting at the same point again. So from 5 milliseconds, I've wasted 4 milliseconds to come back to the original position. So what I'm left with? An extra time of 1 milliseconds. What is it going to do? It takes 2 milliseconds to come down completely. That means half of it, it's going to take at 1 millisecond to come at the center point. So all these particles are going to come at the center after that first millisecond. So what will be the line? What is the line going to look like? The line will look like a flat line. This, you can go into the marking scheme and check for May-June 2017, paper 21, question number 24. It will say that there will be a line at the center, with no amplitude. How has that happened? Because all of these particles have come down to the mean position. These have come up to the mean position in 1 millisecond. These have come down at this point to form the mean position in a time frame of 1 millisecond. I hope that we understand how to tackle this question or these type of questions.